Welcome back to a video series on MAC 1140 Precalculus Algebra. My name is Sean Perry. These are guided notes number 13 in the series on section 3.1, matrix algebra. So let's begin by talking about a simplified interpretation of what a matrix is. We're not going to talk about all the things matrices are good for right now. We're not going to talk about every way you can interpret what a matrix is. We're just going to talk about a matrix as a grid of numbers. So we think of a matrix as being a rectangle. We think of this rectangle as having a certain number of rows and a certain number of columns. And so these rows and columns give me positions in which I can put numbers. And we can count here and see that there are 5 rows and 2 columns into which numbers have been put. We demark the sides of the rectangle with these brackets like this, and then we fill up the positions inside the rectangle with things. In this case, we're going to fill them up with numbers. And so we would describe this as a 5 by 2 matrix. Those would be the dimensions of the matrix. And in general, we'll describe the dimensions of a matrix as being the number of rows by the number of columns. Essentially, we just want to report those 2 values, and we will demark it in this way. And one of the main things we're going to do with matrices is we're going to define an algebra for them. In other words, we're going to define a way of adding, subtracting, multiplying, and even, yes, dividing by matrices, although we're going to look more at multiplying by a reciprocal or an inverse matrix rather than division the way that we normally think about it for numbers. But first, we have to define what we're going to mean by these things. And unfortunately, without a whole lot of background, it becomes a little bit difficult to describe why we have the particular operations for matrices that we do. If you're interested in seeing, for example, why do we define matrix multiplication and division the way that we're going to, I suggest taking a course in linear algebra, where this kind of operation can be substantiated and the story completely told. For this class, I can only take enough time to tell you how to do these things and not why they are the way that they are. For matrix addition, the sum of 2 matrices A and B, we need them to have the same dimension. In other words, if A is a 1 by 5 matrix, the dimensions of B must also be a 1 by 5 matrix. And the reason is we're going to define addition pairwise. By pairwise, what I mean is that we're going to look at numbers which are in the same position in the 2 corresponding matrices that we're adding, and we're going to add those numbers. So for example, these 2 matrices have dimension 4 by 2. This is a 4 by 2 matrix. This is a 4 by 2 matrix. And the sum is also going to be a 4 by 2 matrix, where each entry is going to be the sum of the corresponding entries in the first 2 matrices. Let's call them A and B. So if this is A and this is B, this one that I'm writing now will be A plus B. And so here we might call this entry 1, 1, row 1, column 1. Entry 1, 1 in our A plus B matrix is just going to be the sum of the 2 entries in position 1, 1 in the 2 first matrices. And likewise, we're going to do the exact same thing in each other position. If I'm in position 2, 1, then I'm in the second row first column, and we would take 5 from matrix A and 8 from matrix B and sum them. And now we just want to carry on in that fashion to get the following entries for our matrix A plus B. Now, of course, that can all be simplified by just doing the operations that we've listed here. And so this sort of gives us our first glimpse as to what the utility of a matrix is. And if nothing else, it lets us encode a large number of algebraic or arithmetic operations very compactly. And it gives us a way of doing many operations simultaneously. Problem 4 asks us to add some more matrices, but first we have to figure out which ones can be added. Let's write down their dimension to see which ones match. Here I have a 3 by 2 matrix. Here I have a 2 by 2 matrix. Here I have a 3 by 2 matrix. And here I have a 2 by 3 matrix. Only 2 of these match, which are matrices A and C. So let's write down what is the sum of A and C. In other words, what is going to be the sum of these two matrices. Again, we really just want to take the pairwise sum of each entry. So for example, in the 1, 1 position here, I'm going to take entry 1, 1 here, entry 1, 1 here, and add them together. To get this position here, which is 1, 2, I will take the 1, 2 position here and the 1, 2 position here and add them together. And so on and so forth, which we can evaluate to give us the following matrix. Before we move on, I would like to show you how to enter matrices into a TI graphing calculator. To access your matrices and different matrix commands, we're going to go here to the matrix window. So click on second and this button to get to matrices. Here we have names of the matrices we can use. We're going to go over to edit and click on the first matrix. We want to first put in its dimensions. So I'm going to make a 3 by 2 matrix, and I'm going to input the corresponding values for matrix A. Once I've put each of these in, we have matrix A stored in our calculator. If I quit and go back into matrices where it says names, you can see A appears now, and clicking enter a couple times, it will display that matrix. Let's make sure all our entries are correct. I think it looks good. So now let's go back into matrices and edit matrix C. Again, I want this to be a 3 by 2 matrix with the following entries. Now, if I ask it to take matrix A and add to that matrix C, it will do so. This will be more useful when we look at other matrix operations that take a bit longer than finding a sum, but it's good to know right off the bat how to enter a matrix into the calculator and how to do basic operations with them. To subtract matrices from each other, we're also going to work in a pairwise fashion, although I must admit I rather prefer to define A minus B as being equal to A plus -1 times B, for reasons I've addressed in my previous videos on intermediate algebra. But we haven't yet defined what it is to multiply a matrix by a number, which we're going to do presently. But for right now, I'll just say that we can also define subtraction in a pairwise fashion. That is to say, if I want A minus B, I go to each entry in this new matrix, which will also have dimensions 2 by 3, as both of these do, and I will calculate the entry in each position by looking at the positions in the corresponding first two matrices. For example, position 1, 1 will be -3 minus -5, and so on. Now we just want to evaluate those to get the resulting difference of the two matrices. Of course, once you get a little bit more comfortable with this, for simple things like addition and subtraction, there's really not much of a reason to do so much work. If you can do 7 minus 4 in your head, you can do this matrix subtraction in your head. 5 minus 8 is -3, -6 minus 1 is -5, and so on. We just need to make sure that we are matching the pairs of entries in their respective positions in the two components of the difference, and then we make that entry in the difference matrix the difference of the entries. So for example, -2 minus 3 is going to give me -5, and so on. Now we're going to talk about scalar multiplication of a matrix. So before we talk about the multiplication of matrices, which is going to be very different than the multiplication of numbers, we are going to talk about the multiplication of a matrix by a number. And essentially all that we're going to do if we are multiplying a matrix by some scalar number is we are going to multiply every entry by that number. And so we will get a matrix that is the exact same dimensions as the matrix that we started with, where each entry has just been changed by multiplying it by this scalar number. Now, the use of the word scalar here is just to distinguish it from things like vectors, which are a kind of matrix, or other things which have more dimensions than 1. You might be tempted to think that a scalar, like 3, could really just be identified with a matrix that only has one entry, a 1 by 1 matrix, if you will. And that is true to a certain regard. But when we talk about matrix multiplication, which we're going to soon, we have to have a certain kind of matching dimensions condition in order to make it happen. And looking at a number like a 1-by-1 matrix, scalar multiplication is not matrix multiplication by a 1-by-1 matrix. I'll clarify that a little bit more as we go into matrix multiplication, but for right now, you should just know that multiplying a matrix by a scalar is different than multiplying two matrices, and all we have to do to multiply by a scalar is multiply every term in that matrix by that scalar. So, for example, if this is my matrix A, then the matrix -2 times A is going to be given by taking -2 and multiplying it by each entry in our matrix. Carrying out these operations, we get the following result. So matrix multiplication is something else, something we will look at presently, but scalar multiplication of a matrix is a very simple process, something that we could do in our heads just by looking at a single operation against each entry in the matrix. So somewhat simpler even than adding two matrices together, where we might be adding different numbers each time. Here I'm multiplying by the same number each time. It really is that simple. Now, of course, we could combine these two operations together. If I multiply this matrix by 5, I multiply each entry by 5. And if I multiply this one by 4, I multiply each entry by 4. And taking the sum of these two means taking their pairwise sum. So for example, 10 plus -40 is -30, and so on. We could also define a matrix to have the entries as given, and define its companion matrix in the same way. And with these entries in place, I could just write what is 5 times my matrix A plus 4 times my matrix B, where I've stored the other matrix, to have the calculator do such an operation for me. Before we dive into examples of matrix multiplication, I just want to give kind of an overview of it. First of all, why it looks the way that it does has to do with how matrices can be interpreted as a kind of function on a space of vectors, which you could think about as a list of numbers, and the way that those functions are composed with each other has to correspond to this particular kind of matrix multiplication. Again, if you want more information on that, there are entire courses, in fact, a whole sequence of courses on this kind of analysis of what a matrix is. For now, I will just say the following things. If we want to multiply a matrix A times a matrix B, we're going to have the following conditions be met. A could be a n by m matrix in its dimensions. Then B's number of rows has to match A's number of columns. So these two numbers here must match each other. And then this other number here could be whatever we like, let's say P. Now, by the time we're done with this process, we are going to sort of eliminate these middle numbers. These two will disappear or contract, as we say, and the result is going to be a matrix which has dimensions n by p. So notice we need the m's to match. We need the number of columns of A to be the number of rows of B. And when we're done, A times B is going to have the dimensions n by p, or the number of rows of A and the number of columns of B. So let's say A has n rows and m columns. And let's say B has m rows and p columns. The way that we find a given entry in the product matrix, which is going to have n rows and p columns, is going to be as follows. Let's consider an arbitrary element. We'll call this C. And let's say we are in the ith row and the jth column. So we'll call this position Cij. That will be the number that goes into the ith row and the jth column. To find this entry, we are going to look at the ith row in matrix A, and let's say that has the following entries. Let's say that's AI1 and AI2 and so on, all the way up to AIM, where this is the ith row mth column. And then we're going to look at the jth column in matrix B. And let's say that has the following entries. Let's say B1j and B2j and so on, all the way down to the final entry, BMJ, where this is now in the nth row and still the jth column. Then the way that we are going to calculate Cij is in the following way. We are going to take a pairwise product between each thing in these two lists, and we're going to sum them. So for example, I'm going to take AI1, I'm going to multiply that, let's circle these so we can see where they are, and I'm going to multiply that by B1J. So the first entry in this row here, I'm going to multiply by the first entry in this column here. That's this element right here. And then we are going to add to that the next pair. So I'm going to take AI2 and B2J. And I'm going to multiply those two together to get some number here. And I'm going to add that to the first product. And we're just going to keep doing this the entire way down. And maybe now it's sort of clear why we needed that dimension matching if this is going to be our definition of how things are going to go, because I need there to be the same number of things in this row, in other words, the same number of columns in matrix A, to match the same number of things in this column here, in other words, the number of rows of matrix B. The number of columns of A and rows of B have to match so that each one of these has a pair that he can partner up with. And then we're going to multiply that pair, and then we are going to sum all of those products. And we'll have to do this kind of process for every single entry in the resulting product matrix. Every single one of those things, and there will be, of course, n times p of them, I'll have to do an operation that looks like this: a row times a column pairwise and summed to give me a single entry. Now, sometimes that might contract down to a single number. Notice here we have a 1 by 3 matrix times a 3 by 1 matrix. The number of columns here matches the number of rows here. And the idea is that when we're done with this multiplication, these two numbers are going to contract and disappear, and all we will have left is a single 1 by 1 matrix, which does have a correspondence with a single scalar number, but we are going to interpret that as a slightly different object. So let's see how to get that object. Let's see what happens when I take the product of these two matrices. What I need to do is I need to get the pairwise product of everything in this row with everything in this column. So we're going to take first, for example, 0 times 7 plus -2 times 4 plus 3 times 3. And this is one operation. We're going to get a single number from that. We'll have 0 times 7, which is 0, plus -8, plus +9. So we just get a 1 here. Now, this process of multiplying a row by a column pairwise and summing them, we're going to have to do that for every entry in a given product matrix. And there might be many such entries. For example, here, if I have a 2 by 3 matrix, and I'm going to multiply that by a 3 by 4 matrix, we're going to lose the column and row dimensions here, and we are going to wind up with a matrix that has 2 rows and 4 columns. In other words, I'll have to do this kind of above process 8 times in order to complete the matrix multiplication. Number 12 says, can we perform a certain matrix multiplication? And the answer is no. We have a 3 by 5 matrix, and we have a 6 by 4 matrix, but the number of columns of A here and the number of rows of B don't match. And so we cannot multiply. Matrices cannot all be multiplied by each other in the same way that we cannot add every matrix together. We had to have perfect dimension matching in order to add. We have to have this kind of dimension matching where the number of columns of A and the number of rows of B match before we can multiply. And before we do another example, I just want to point out something that might be apparent to the person who's thinking about what they're listening to right now, which is that matrix multiplication cannot be commutative. That is to say, if I have n by m, and that's my matrix A, and I have m by p, and those are the dimensions of my matrix B, then the dimensions of A times B will, of course, be n times p. But that doesn't mean at all that I could do B times A. B times A, well, we would have to answer the question, does n equal p? If n equals p, then we would be able to perform this multiplication. But if n didn't equal p, then b times a would be undefined. And even if we had something like, I don't know, one of these was a 2 by 3 matrix and the other was a 3 by 2 matrix, right? If that was my matrix A and my matrix B, then matrix A times B, which we can also just write with adjacency of AB, this would have dimensions of 2 by 2. But on the other hand, if I said, what is the dimensions of the product in the other direction, B times A? This is a completely different matrix, although in this case, now it's going to have dimensions 3 by 3. So not only are the products A, B, and BA different than one another, they have completely different dimensions. So we can see that this definition of matrix multiplication, even though it's composed of commutative operations like addition and multiplication, it is not itself commutative. You cannot just do it in any order, and that's going to be something very distinct about the algebra of matrices. Multiplication is a non-commutative operation in matrix algebra. So now let's do a couple examples of matrix multiplication, if such thing is possible. If I want to multiply this matrix, well, yes, we can. They're both 2 by 2s. And so if I have a 2 by 2 times a 2 by 2, I wind up with another 2 by 2, right? If we multiply these two together and these two together, these dimensions contract, and we wind up with a 2 by 2 matrix. So that's going to be just fine. And in fact, this gives us an interesting property, which is that if we have a square matrix, in other words, the number of rows and the number of columns are the same, and we multiply that by another matrix of the same kind, we get another matrix of the same kind. We get sort of the same dimensions when we multiply square matrices by each other. Okay, so let's actually do it. How do I get the entry that goes in the upper right-hand corner? Well, I need to take the row here, the first row, and the column here, the first column, and I need to multiply them together. So we multiply by them pairwise. In other words, we'll do 3 times 1 plus -2 times 2, going down the row and going down the column. And that will be our first entry. Then let's proceed to do another one. Let's say I want to do the first row, second column. We go down this row and down this column, multiply pairwise and sum. So that'll be 3 times 3 plus -2 times -4. Going down to the next row, I'll go back to the first column, and I will go down that row and down that column to find the thing in the second row, first column of my product matrix. This will be 5 times 1 plus 3 times 2. And finally, going down the second row, going down the second column, I'm going to wind up with 5 times 3 plus 3 times -4. And then we could just evaluate each one of these things, which gives me the following 2 by 2 matrix. We note that we could also store these values in the calculator, both as matrix A and matrix B, shall we say. And once we get our matrices updated, we could write matrix multiplication by just writing them adjacent to one another like this. And your calculator will know that this means matrix multiplication. And that's that. Remember to check to see if two matrices can be multiplied. We just need to check their dimension. This is a 2 by 2 matrix, and this matrix has 2 rows and 3 columns. So yes, such a matrix can be multiplied because these two match, and we are going to get a resulting 2 by 3 matrix. What will such a matrix look like? Well, we're going to take the row of one and the column of another and multiply them. So here we would have the following operation to carry out. And we're going to just repeat that in every entry. First row, second column, first row, third column, and so on. So second row, first column, second row, second column, and second row, third column. If we carry out those operations, we get the following 2 by 3 matrix. Is multiplication possible for number 15? Well, this is a 2 by 3 matrix, and this is a 3 by 1 matrix. So yes, these middle numbers match. Matrix multiplication is possible, and our result is going to be a 2 by 1 matrix. That is to say, 2 rows, 1 column. First row, first column gives me 2 times 6 plus 1 times 1 plus 4 times -3. And the second row, first column, gives me 0 times 6 plus 3 times 1 plus 6 times -3. And if I carry those operations out, I get 12 minus 12 and 1, so this is just a 1. I get 0 minus 18 and 3, so this will be minus 15. There we have it. Here we have a 3 by 2 matrix. And can I multiply that by a 4 by 1 matrix? No. 2 does not equal 4. These do not match, and so we cannot multiply these two matrices together. Likewise, with 17, we should check our dimensions. We have a 2 by 1 matrix, and over here I have a 1 by 4 matrix. And so yes, we are going to be able to multiply these together because these two numbers match, and our result is going to be a 2 by 4 matrix. So let's get 2 rows and enough space to put 4 columns here. And let's write down what we would get. Our first row, notice a row only has 1 entry here. And our first column, which again only has 1 entry here, is going to go in our position 1, 1. So that's going to be 0 times 5. We're going to proceed in a similar way for each one of these. We'll have 0 times -2, 0 times 0, 0 times 4. And then down to the second row, we'll have 3 times 5, 3 times -2, 3 times 0, and 3 times 4. Of course, this is going to give me all zeros along that top row, a 0 in this position, and the following values in the other positions. So sometimes this can be rather brief. If there is only a single element of this row and a single element of this column, we wind up with just simple multiplication in each entry. Not really much of a sum to take at all. So when we talk about an identity matrix, we're talking about something like the identity of multiplication. Remember that the element 1 is going to be something which we can multiply by a given number, and it doesn't change it. It gives me the same thing back. What we're going to look for in terms of an identity matrix is going to be something that I can multiply by a matrix A, which will just give me a matrix A back. But the idea is that this is going to have to look different for every single matrix A. For example, if my matrix A is a n by m matrix, then I'm going to need the identity element to have a certain look if this over here is also going to be an m by n matrix and thus unchanged. We'll have to have n here so that they match, and we'll have to have an n here to match up with this n. Now that means that all the identity matrices are square, and we're going to need, so we will identify that dimension of the identity matrix by a subscript n here. Furthermore, we're going to have to preserve each entry of matrix A under this multiplication. And the matrix which is going to do precisely that is going to be the n by n matrix, which has 1s down the diagonal entries and 0s everywhere else. So the way I'll show that is in the following way, with these ellipses showing that the pattern continues. Another way that you'll frequently see that is by showing 1s down the diagonal like this, and then sometimes people will just put big zeros here to say, well, everything else over on these two sides is going to be 0. That's a little bit more informal notation. This one's a little bit more formal, but the pattern is pretty readily available if we look at some examples. Here we have 1s down the diagonal, 0s everywhere else, and it's a square. So this is actually the identity matrix for 4 dimensions. Here, I don't have a square matrix. I have these extra elements down here. So this is not an identity matrix. Here, we have 1s down the diagonal, 0s everywhere else, so we're good on this one. This is the identity matrix for 2 dimensions. And likewise, we have a non-square matrix here, so this cannot be an identity matrix. I just want to note before we move on that in the same way as with multiplication, for numbers, multiplying on the other side by 1 would still just give us A. For such a matrix A as I've shown over here with dimensions n, m, if I wanted to multiply on the other side, I would actually need a different identity matrix possibly in order to do that. Now, if A was square, I wouldn't. But if A is a rectangular matrix, n by m, I'm going to need a different dimension identity matrix if I wanted to multiply on the right versus if I wanted to multiply on the left. And although we're not going to do any more exercises for this video, I feel like this is a really good point in the conversation for me to address what is the division of matrices. What would it mean to take a matrix A and divide by it? Could we come up with some kind of sense of this? And the answer is yes, we can. We're going to define that as being B times the inverse matrix of A. And what is an inverse matrix? Well, in a similar fashion to how we define reciprocals for numbers, where A to the minus 1 is the number such that A times A to the minus 1 just gives me 1. A number times a reciprocal is itself. That's the formal definition of a reciprocal. In the same way, A inverse of matrix A, where we're going to require A to be a square matrix for now. We could define this for n by m matrices if we wanted to define left and right inverses respectively. But to talk about just a generic inverse, we're going to have to be talking about square matrices. And in that case, we're looking for something, an is the matrix such that if I take A and multiply it by A inverse, I wind up with the identity matrix for that dimension. So we want to be able to find such a matrix, and we're going to look at some various methods of doing that in the next video. For now, that's going to be it for this one. Thank you very much for your patience. Good luck with your studies. I'll see you in the next one.